Hey everyone, Mr. Fransky here. I'm still dealing with some technical issues, so I am once again going to have to deal with a computer where I can't write. So I'm going to try to use the laser pointer today. Look at that. Isn't that fancy? So today we're talking about 9.2a, which is an intro to Taylor series. And Taylor series are really going to drive the work we're going to do in the rest of Chapter 9. They're pretty cool functions that mimic other functions, and we've already seen that with some geometric series, some power series. But these are going to be a very specific kind that will work for any function, right? Because we've really been focusing on ones that look like this, like an a over 1 minus r. Today we're going to focus on anything, really. We're going to be able to create polynomials like we have down here for anything. So start with some bell work. You can probably do a and b on your own. C, I think you could probably do if you give it some time. But if you want to do it with me, that's just fine, too. So for letter A here, I want you to write out the power series for 1 over 1 plus x. And we talked a lot about this in 9.1b. We did a lot of functions that look like this. This is an a over 1 minus r kind of situation. You want to find out what a is, what r is. I want you to write me the first few terms and the sigma notation for the series that represent 1 over 1 plus x. And then the question is, can you use it to find the series for natural log of 1 plus x? This is kind of the last thing we talked about in 9.1b, where we use calculus to be able to kind of change some functions to other ones that are not necessarily geometric. And give me the radius of convergence for both of those. I also want you to do the same thing for 1 over 1 plus x squared. This is another thing that we got to in the 9.1b video. So you might already have done this, but if you want to try it again, you can. So this is another a over 1 minus r situation. And then the question is, could we use that to somehow find the power series for tangent inverse? And then letter C here, I want you to find the coefficients, a0, a1, a2, a3, and a4 of the fourth degree polynomial here, where p0, p prime of 0, p double prime of 0, p triple prime, and the fourth derivative are all equal to 1. So these are going to have to be something very specific in order for those derivatives all to equal 1. What I would suggest doing is just write out the derivatives first. So it would p prime of x be? What would p double prime of x be? P triple prime of x. And then plug in 0 to all of those, and then figure out what the coefficients have to be to make it 1. So let's jump in. Let's give them a shot. So first, the power series for 1 over 1 plus x. We've seen this so many times. This is an a is 1, and an r that's negative x. So we're going to have a power series that looks like this, right? So the first term is 1, then we have minus x plus x squared minus x cubed. This, of course, is only good when the absolute value of x is less than 1, right? Because we need that r value to be between negative 1 and 1. The sigma notation for that, I started at 0. I'll be starting all of my sigmas at 0 today. Negative 1 to the n. You could just write this as negative x to the n. My guess is that's how most of you would do it. Generally, if any series alternates, what I'm going to do is do a negative 1 to the n in front, because then I just don't have to worry about the signs at all. Then I can just look at the x's or whatever my terms are, and I can just focus on those. So we have 1, that'd be x to the 0, then x squared, x cubed. We're just getting x to the n as n goes to infinity. That's, of course, good for x between negative 1 and 1. So now to use this to find natural log of 1 plus x, that is the antiderivative of 1 over 1 plus x, right? Technically, we have an absolute value, but because the absolute value of x is less than 1, that means that x between negative 1 and 1, so this at the very smallest is going to be just bigger than 0, right? Because if this is for sure bigger than negative 1, then this is not going to get down to anything below 0, so it's positive for sure. So we antiderive the left side, we antiderive the right as well. We talked about this in 9.1b. We're just doing anti-differentiation term by term here. So we anti-differentiate the left side, we can integrate the right side as well. So 1 goes to x goes to x squared over 2, x squared goes to x cubed over 3, x cubed to x to the fourth over 4, etc., etc. And in the notation here, for the sigma, all we have to do is just anti-differentiate x. And I've had some people ask me, well, don't you have to deal with the negative 1 to the n here because there's an n there? Remember, we're doing this based on x, not on n, right? So this is technically a constant for every single one of those terms. So we only have to worry about the x. So your x to the n turns into x to the n plus 1 divided by n plus 1. And this radius of convergence is going to be the same. We're actually going to learn in 9.2b that the interval is a little bit different for this one because it's an alternating series. That kind of makes it a little bit special. But for now, just know that whatever the radius is that we started with is going to be the same as the radius that we finish with. All right, moving on to that tangent inverse. So we're going to start with a series for 1 over 1 plus x squared. So this is another geometric with an a that's 1 and an r that is negative x squared. It's going to look like this. It's going to be 1 minus x squared plus x to the fourth minus x to the sixth. We're just going up by the even powers of x, and it's alternating. So the sigma for that, negative 1 to the n, notice I have that again because it's alternating. And then x to the power 2n, because that's going to give me all those even powers, right? 2, 4, 6, 8, we appreciate. Right? So then if I want to use this to get tangent inverse, well, same as last time, right? Tangent inverse is the antiderivative of 1 over 1 plus x squared. If you integrate this, that equals tangent inverse. So if I want to integrate the left side, I should integrate the right side as well. So integrate the left to get tangent inverse, integrate the right, we get x cubed over 3, x to the 5th over 5, x to the 7th over 7. It's all the odd powers, right? Because we're going up by 1 from all the evens. So if we just think about this from an integration standpoint, you add 1 to the exponent here, and you divide by the same thing, right? And that's it. This is also kind of a good thing to know, is if you want to get all the odd numbers, 2n plus 1 is a good way to do it. You could also do 2n minus 1, but if you did that in this case, you would have to start at a different n value. I think you'd have to start at 1 if you did 2n minus 1. Yes, I think that would work. So again, I don't care how you do your sigma notation, as long as you end up generating the correct term. So it's always good to kind of plug in some n values and make sure that it's creating the series that you want. All right, so now we're going to do 3 problems that kind of focus on this polynomial. And I'm going to start with this one where it's just all of the derivatives are equal to 1. We're going to get faster at this as we move on. But the first one, we're going to be very methodical and very careful about how we do this. So what we have here is a 4th degree polynomial, and I increased the powers. We talked about this the other day. We said generally you see these in the opposite order, right? You see the 4th degree, then the 3rd, 2nd, the 1st, and then the linear, or the constant. But since we're talking about infinite series and they're getting bigger, it makes sense to start with the constant and then grow. So in this case, what I'm going to do is I'm just going to plug 0 into the function. So we take a look at the functions. The function itself, a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th. They tell me p of 0 is 1. Well, when I plug 0 into the function, what does it become? All of these x's cancel out. In fact, that's going to happen for a lot of these. If you actually tried this on your own, and I would encourage you, even if you haven't yet, give it a shot, because it's not that hard. But if you plug 0 into the function, what happens? All you have left is a0. So a0 must be 1, right? Because they tell us p of 0 is 1. So when all these other terms cancel out, I need that constant term to be 1. So we've already got one of them, right? We only have 4 to go, excuse me. Okay, now p prime of x, if you do that, the a0 disappears, because that's a constant. a1 is all that's left from the x. This 2 comes to the front, so we have 2a2x, then we have 3a3x squared, and then we have 4a4x cubed, right? But if we plug in 0 into this derivative, once again, everything with an x is going to disappear. All we're going to have left is this a1. So when we plug 0 into the derivative, all we have left is a1, and we need that to be equal to 1 as well, because it tells us that all of these derivatives have to be 1. So a1 must also be 1. 2 down, 3 to go. The second derivative, now we have 2a2, right, because the x disappears, because the derivative of that linear term is just going to be the constant in front of the leading coefficient. And then here we have 3 times 2, and you'll see why I'm doing this in a second. Because if you keep taking derivatives of polynomials, these powers are going to keep stacking, right? So 3 times 2 times 1, here, 4 times 3 times 2. If it kept going, you would have, like, every one of these numbers would just be multiplied by all of the ones below it, right? And that's going to be kind of a little bit foreshadowing for what's to come. So here, this time when I plug in 0, everything with an x still disappears, but I'm not just left with the constant. I'm left with this 2. Where did this 2 come from? It came from the fact that it was squared initially. It's now come to the front. So here we have p double prime of 0 is 2a2. So therefore, a2 must be 1/2, because I need the product of these two things to make 1. Right? I need 2a2 to be 1. So a2 must be 1/2. All right? Third derivative. So now, the 2a2 is gone, because that was our constant of the last one. Now we have 3 times 2 times a3. This x disappears. Here the 2 joins the ranks of the 4, 3, 2, and we should have a4x left over. We plug 0 in here, because we're plugging in p triple prime, of 0. This term is going to disappear, and we're going to end up just with 3 times 2 times a3. So this product right here needs, once again, to be 1. So I need a3 to divide out that 3 and that 2. And yes, that's 1/6, but bear with me, right? If you were to keep doing this, if you were to go to 5th, 6th, 7th, this pattern is going to keep going on, right? The fourth derivative, now this constant goes away, and we have just the coefficient in front of the x here. So we have 4 times 3 times 2 times a4. So that means a4 must be 1 over 4 times 3 times 2. What are we gaining on the bottom here? There's something that this is called, right? This looks like a factorial, right? We're multiplying each one of these powers because they come down and down again, and down again, and down again. We've stacked them up, and we've ended up with kind of a factorial of the highest power. And if you were to keep going with this, it would keep happening. Sometimes I liken this to kind of the Goldilocks story. It's like at any given derivative, all these x's that are still here, those are like too much, right? Because when you plug in the 0, they go away. All of the constants that have disappeared, those weren't enough, right? And then we have this one term every time. That's like the Goldilocks term, right? That's the one term that matters. It's the one that's just right, right? And that's the one that is going to create these coefficients every time. So our polynomial, right, all I did was take those a0, a1, a2, a3, and a4, and I put them where they belong. So we have 1 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over 4 times 3 times 2. And if you think about it, when you derive this, every time the constant will fall away, and you'll end up with one of these powers coming down and canceling with one on the bottom. And eventually, by the time you get to it to be the most important one that actually matters for when we're plugging in 0, you're going to end up just with 1 left over, because everything else will have canceled out. So I was hinting at this before, but all this is just dividing by factorials, right? This is 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. And even, really, these are also divided by factorials. 0 factorial and 1 factorial are both 1 by convention. It's kind of weird to think about 0 factorial being 1, but this is exactly why we need 0 factorial to be 1. There's also some stuff in combinatorics that requires it. But in this case, we see if it was anything else, it wouldn't create this 1 right here. So just remember, n factorial is just, you multiply the number by the number below it again. Oh, that should be an n minus 2. Let's fix that right now. Let's see if they're going to let me out of here. There we go. So this should be an n minus 2. That's my fault. There we go. That's going to mess up my animation, but that's okay. Okay, so n factorial, n times n minus 1, n minus 2, n minus 3, and then all the way down to 3, 2, and 1. And notice I don't have any 1s up here, but you don't really need the 1, right? Because multiplying by 1 doesn't do anything. All right, so let's try one with some more interesting values. So we're going to once again make a fourth degree polynomial. P of x is a0 plus a1x plus a2x squared, a3x cubed, a4x to the 4th, where p of 0 is 3, p prime of 0 is 2, p double prime is 7, p triple prime is 17, and p4 is 11. So I chose more interesting values this time instead of 1, but it's still going to really work out the same way. So this is the exact same thing I had on the last slide, right? All of our derivatives are still the same. P of x, p prime of x, p double prime, p triple prime. We still have this Goldilocks scenario. There's a bunch of terms with x. There are a bunch of terms that have already fallen away because they've already become constants and disappeared. And we still have this a0, a1, then we have 2a2, 3 times 2a3, 4 times 3 times 2a4. And so what we're going to do is I'm going to look through these kind of one by one again. So p of 0, once again, is just a0. All of these x terms disappear. So that a0 is just going to be 3 because that's what I want it to be. P prime of 0, I just end up with a1. That means a1 must be 2 because I want that p prime of 0 to be 2. P double prime, this is where it gets interesting, is 2a2. I want 2a2 to be equal to what? I want it to be 7. So that means that a2 must be 7 halves. Okay? The triple prime is going to be 3 times 2 times a3, right? Because the x term is going to disappear because we're plugging in 0, right? It's important that we're plugging in 0. If we're plugging in a number, then we would have this giant system. It wouldn't be good, right? We're plugging in 0, nothing, so everything disappears. So this means a3 must be what I want, 17, divided by that 3 times 2. The fourth derivative of 0, we just have 4 times 3 times 2 times a4. So that means if I want 11, it must be 11 over 4 times 3 times 2, because then the 4 times 3 times 2 will cancel. Basically what I'm doing here is there are mechanics of the polynomial that I need to ignore. I don't want to deal with all these exponents that are up here, so we divide them out every time. And then whatever I want, I just stick it on top of it. So all these factorials on the bottom, I just stick what I want right on top of them, which is really the moral of today. We're going to get to it in a second, but all we're doing is dividing by factorials. That's really all there is to it. So p of x is going to be 3, that's our first term, plus 2x right here. And then p double prime is 7, so I have 7 over 2 factorial. Then I have 17 over 3 factorial. Then 11 over 4 factorial. And invariably, every time, someone always says, wait, I don't understand why the factorials are there. And it's just to make the exponents disappear, right? I want this to happen. I want these to be my derivatives. So I don't want to have to deal with the 2 and the 3 and the 4 that are coming down as I'm taking derivatives. I want those to disappear. So as the 4 comes down, it cancels. Then the 3 will come down, it'll cancel. Those things will keep on canceling until I get to the exact term that I actually care about, the actual one that I want. Okay? So, you notice how we can make these quickly now. All we do is we take whatever we want for the derivatives to be, and we stack them up on top of these factorials. That's all there is to it. It seems too simple, and sometimes I think it is. It's like, how can this work so well? And I almost wonder if the creators of calculus stumbled upon this, and then they realized how well it works. And you're going to see some incredible things towards the end of this video. And it's like, wow, this really works really well. And so it's simple to do, but you just have to remember how to do it. You put the values on the top that you want, and you divide by the factorials. That's what others do. So let's try the same thing with a function now. So I'm not going to give you the derivative values. We're going to have to find them. So once again, we're going to try to find a fourth degree polynomial, p of x, it's the same thing we looked at before, that mimics the first four derivatives of this function, natural log of 1 plus x. So what I'm going to do is I'm actually going to look at those derivatives first. So the function value, first of all, itself, f of 0, if you plug 0 in here, ln of 1 is 0. Remember, if you ever forget about natural log, draw a graph, right? And you can see when the x value is 1, it crosses through the graph at 0. F prime of x. So the derivative of natural log is 1 over whatever's inside. So it's 1 over 1 plus x. We don't have to worry about chain rule because the derivative of the inside, the baby here, would just be 1. And so f prime of 0, right? We're trying to mimic the first four derivatives of this guy. So f prime of 0, if I plug 0 in here, I get 1. So really what's happening here, I'm getting these values. These values are going to represent what I gave you last time, right? So last time I gave you the values. This time I'm actually having to figure them out because I'm dealing with a function. The second derivative now, I would think about this as in 1 plus x to the negative first power. The negative 1 will come to the front and will drop to a negative 2. So here's the negative. And there's my negative second power. It puts me to the square on the bottom. So the second derivative of 0, when I plug in 0 here for x, 1 squared is just 1. I have negative 1 over 1, which is negative 1. The next derivative, so we think about this as a negative 2 exponent. That'll come to the front. The negatives will cancel. We'll have a positive 2. I'll put that up on the top. And then on the bottom will become a negative 3. So we have a third power on the bottom now. So we have 2 over 1 plus x quantity cubed. So the third derivative here is when I plug in 0, I'm going to get a 2, because that 2 is just sitting up on the top. The fourth derivative, if this is a negative 3, it's going to come to the front, multiply by the 2, and it gives me a negative 6, and then I'll have a fourth degree on the bottom. So there's my negative 6. I have 1 plus x to the fourth on the bottom. So when I plug in 0, here I get 1 to the fourth, which is 1, and then negative 6 over 1, which is negative 6. So what I'm trying to do now is I'm saying I want this polynomial. Because really, we've been talking about this with geometric series already. We're trying to find a polynomial that does a nice job of replicating this natural log 1 plus x. And so to do that, the method we're using is saying, well, let's make it mimic all the derivatives. And let's just see if that creates some kind of a function that works well. So we have these derivative values now that are all given at 0. F of 0, f prime of 0, f double prime, triple prime, and then the fourth derivative. And if we look at our polynomial now, I'm just going to take these values and set them on top of the factorials like we did in the last example, right? So 0 is over 0 factorial technically. 1 is technically over 1 factorial, but that's just 1. Negative 1 is over 2 factorial. 2 is over 3 factorial, and negative 6 is over 4 factorial. And the reason I'm dividing by the factorials again, I'm sorry if I sound like a broken record, but I think it bears repeating. That means when I take the derivatives here, the powers that will have come down will cancel out. All I'll be left with is the value that I actually care about, the value that I actually want. Everything else will cancel out and be gone. So now, we can do some algebra here. So, negative 1 over 2 factorial, that's negative 1/2. 2 over 3 factorial, remember 3 factorial is 3 times 2 times 1. The 2's cancel, so it's just a 3 on the bottom. 4 is 4 times 3 times 2 times 1. 3 times 2 is 6, so those actually cancel out. All I'm left with on the bottom is 4. When I did this problem the first time, I kind of thought, well, that's interesting. It's like the factorials on the top are like one behind, right? Because if you think about it, what's happening is this power on the bottom keeps stacking in the front. So we got a 2, then we got a 3, then we got a 4, next we get a 5. But it's kind of like one behind because we started with this natural log. We didn't start with a fraction. So it's like one behind what we're at. So if you were to come up with a general term here, the top would always be like n minus 1 factorial. Right? So we have 4 factorial here. This is like 3 times 2. The next one would have 5 factorial on the bottom. The top would be 4 times 3 times 2. They would cancel out with most of it on the bottom, but the 5 would be left. This should look familiar, right? We've seen this before. We actually did this problem in the Bell work a little bit different way, right? Let's see if I can find it. This one. Yeah. So we see that I have the natural log of 1 plus x. It's exactly the same function, which is kind of cool. So we did this. This was entirely done using the derivative, the antiderivative of a geometric series. Now, we did this a totally different way. We mimicked the first 4 derivatives, and we ended up with exactly the same function, which is kind of cool. And this pattern will continue on. Wow. Fun stuff. Okay, no more of these 4th degree polynomials, I promise. we're going to kind of find a general way to talk about this now. So we're going to talk about a Taylor polynomial and a Taylor series. So what we've been creating here is really a Taylor polynomial. What a Taylor polynomial does is it mimics f of x through n derivatives. So the nth degree or nth order Taylor polynomial for a function f of x is a polynomial of degree n that mimics f of x through n derivatives. So what we just had was the fourth degree or fourth order Taylor polynomial for f of x equals natural log of 1 plus x because we made it mimic this function, natural log of 1 plus x, through 4 derivatives. So sometimes you hear people use the order, sometimes you hear them use degree. AP uses them interchangeably, so you can use either one. So fourth order Taylor polynomial for this function. Whoops, what did I just do? I don't know what that was. All right, so the fourth order or fourth degree Taylor polynomial we found by using the derivative values and then dividing out those factorials. And it's this guy right here. Often they call it P4 of x or T4 of x, and they'll define that in the problem. They'll say find T4 of x, the fourth degree Taylor polynomial, blah, 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 whatever. So if the Taylor polynomial is infinite and mimics f of x through all derivatives, it is called a Taylor series. For the function we were just looking at, here would be the sigma notation. The negative 1 to the n is going to make it alternate, right? We have positive, negative, blah, blah, blah. And then we have x to the n plus 1 over n plus 1. That comes from that anti-deriving we had before. You could start this at 1 and then just do x to the n over n. That'd be fine. But we see here we have the second power over 2, third power over 3, fourth power over 4. This is the Taylor series that represents this function, natural log of 1 plus x. So in general, this is the formula for the Taylor series. The Taylor series for f of x centered at x equals 0, which is also called the Maclaurin series. Maclaurin is specific for the center at 0. So sometimes AP will say, find the Maclaurin series. You have to know that that means they want it centered at 0. We're going to see an example of one centered at a different value in a second as well. So what you always do, you do f of 0, f prime of 0 times x, f double prime of 0, x squared over 2 factorial. This is exactly what we're doing in the last few examples, right? We're just taking the derivatives, we multiply by x to the correct power, and we divide by that factorial. So in sigma notation, we go from 0 to infinity, nth derivative at 0, right? Because that's what all these derivatives are. We're just finding the derivatives and stacking them on top of the factorial, and then multiplied by x to the n. So it's really just dividing derivatives by factorials. That is the moral of today, but I wanted you to practice that with the polynomials first, just to see that that's why this works. And remember, 0 factorial is 1 factorial is 1. So technically, these are divided by 0 factorial and 1 factorial, but because they're both 1, we don't write it. Some people get fed up with me also for writing 2 factorial, because like 2 factorial is just 2. Why do you even need the factorial? Well, because it's in the formula, right? I mean, it's n factorial, so you might as well write 2 factorial. Now, I will say this. We don't know much about convergence of these things unless they're geometric, right? So like for that natural log function, I'll back up a little bit to it. So the natural log function, we know that this only converges between -1 and 1 because we found this a different way as well. We found it using geometric. But any other function, we don't really know anything about how they converge. So for now, just know that they're generally good close to the center. So anything you center at 0 will be pretty good close to 0. And they're going to be bad the further away that you get, right? Some of them, we talked about this with power series the other day. We said that some of them converge only at the center. Some of them converge for a small radius around the center, and some of them converge for all x, which we're actually going to see in a minute here, which is kind of cool. Okay, so we're doing easy Taylor polynomial. So everyone always groans every year at me when I say let's find the degree 7 Taylor polynomial for this function, but you're going to see this is so easy because I picked an easy function for you. So what we have to do, if we look at this this idea here, what we have to do is we have to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0. We're going to find the first 7 derivatives of sine. And some of you, your wheels are probably already turning and you're thinking, oh, sine, that's super easy derivatives, right? It's a cyclic function, and we plug in 0, a lot of these things are going to disappear. So let's think about this. So f of 0 we need, right, because that's the first thing in our Taylor polynomial, is f of 0. So f of 0 is just sine of 0, right? What is f prime of sine? What's the derivative of sine? That's cosine, right? So cosine of 0 is 1. Right? Second derivative is going to be a negative sine. Negative sine of 0 is just 0. Third derivative at 0, it's negative cosine of 0, which is negative 1. Fourth derivative at 0 is going to be, we're back to sine now, and that's 0. So you notice we've gone all the way back to the beginning. I think I should have the next 3 all automatically, yeah. So we go 0, 1, 0, negative 1, 0, 1, 0, negative 1, right? These are Pretty boring numbers. Okay, this is why I chose 7th degree, because a lot of these terms aren't even going to exist, right? I'm going to do this to avoid having to click through a bunch of things. But like f of 0 is 0. In fact, if you notice, all of the even derivatives, f of 0, f double prime, f to the 4th degree, f sixth derivative, all of those are 0. So all these even powers, none of them are going to exist, right? And I kind of gave away my punchline because we can see it at the bottom here. But all we do is we take all of these coefficients and we stack them on top of factorials, right? So 0, there's no first term. The first term we're going to have is 1x. There it is. Then we're going to have a negative 1 over x, negative 1x cubed over 3 factorial, because the third derivative is the first one that makes any sense. Fourth derivative doesn't do anything. Fifth derivative is going to be positive 1, x to the 5th over 5 factorial. And then the last one we have in the 7th degree here is going to be that x to the 7th over 7 factorial. Sometimes, poorly written problems, sometimes you see them in the book, they'll say that, like, they'll ask for the 8th degree polynomial for this. Technically, this is the 8th degree polynomial, because the next derivative would be 0, so there wouldn't be a term. So this could be called the 7th order or the 8th order Taylor polynomial. Either one would be fine. And you can kind of see the pattern, right? What would the next term be? It would be plus x to the 9th over 9 factorial, and then minus x to the 11th over 11 factorial. This pattern is going to continue, and if you wanted a Taylor series, you could do that off to infinity. So let's have you guys try one. Let's have you guys try cosine x. So try to find the degree 6 Taylor polynomial for f of x equals cosine x. So you can follow the same pattern I had for the last one. Just find the first 6 derivatives and then throw them over those factorials. All right, let's try it together. So the first thing we need is f of 0, which is just cosine of 0. That's 1. F prime of 0, that's negative sine of 0, which is 0. And then I just jump to the rest because it's pretty much the same as we had last time. So the second derivative is negative 1, third derivative 0, fourth is 1. Notice this time the even ones are the ones that work. The odd ones are the ones that end up being 0. Okay? So our polynomial here is just, the first term is 1, right? Because we have a 0th term this time. And then we have no first term, so there's no x term. And that's going to be a negative 1 x squared over 2 factorial, then a positive x to the 4th over 4 factorial, and then this last one down here, a negative x to the 6th over 6 factorial. Now, some of you may have used our knowledge from 9.1 to actually think, could you see any shortcut we could have used with sine x? I'm going to go back here to our sine. So this is the formula for sine x. How are sine and cosine related? Cosine is the derivative of sine, right? So couldn't we just take the derivative of this function? Let's see if it works. Derivative of x is 1. This x cubed over 3 factorial, if you take the derivative, the 3 will come to the front, it'll cancel with the 3, we're just left with 2 and 1 on the bottom, that'd be x squared over 2 factorial. The 5 would come to the front and cancel with the 5, we'd be left with 4 times 3 times 2 times 1 on the bottom, that's x to the 4th over 4 factorial, and the last one is x to the 6th over 6 factorial. So pretty cool, that actually ends up being exactly what we wanted. Which is kind of cool. So that's the shortcut. Now we're going to take a look at the graphs of these, because again, we don't really know where these converge. A good guess would probably be they converge between negative 1 and 1, because it seems like that's where everything converges. But let's actually take a look and see what happens. So what I've got here, I think this is what I want. Yep. So I've got first just my sine wave graph. Okay, so this is the sine wave. And what I've got here is the first few terms, like up to the 9th order, Taylor polynomial for sine. So first I'm just going to graph x. And as expected, and I'd like to change the color of that. No, that's okay. We'll just stick with red. So, as expected, it's really good at 0, and it's okay for a little while, right? Like maybe until like this is pi over 4 and negative pi over 4. Just that line actually would do a decent job of approximating sine. But we can do better. So if we go to a 3rd degree, look at how well we're already fitting it, right? So we have this cubic polynomial that appears to be fitting into that wave quite nicely. If we go to the 5th degree, notice we change end behavior every time because it's alternating. So this time we go from down to up, the next one will go from up to down. But look how nicely already in between, like negative pi over 2 and positive pi over 2, it's really doing a nice job of mimicking the function. And we know it's only perfect at 0. If you were to zoom in, like on this spot right here, it wouldn't be as good, right? There would be a little gap there. But it's getting quite good, actually. So if we take a look at the next one, now we almost have 1 full period of the sine wave from negative pi to pi, right? That's pretty good. We look at the 9th. Look at this. So negative 1 is like over here, and like positive 1 is like over here, right? So it's for sure doing a better job than any of the geometric series we saw. it's already getting like maybe 3 or 4 times as far out as any of the geometric series we saw. And it's done it very quickly, right? We only had, what, 5 terms here, and we're already really doing a nice job of mimicking this function. So what I have here, I have the general term for sine, and we're actually going to talk about this, right? I'll talk through the general term in the next section. But you can kind of see what's going on, right? We have this -1 to the n, that's going to make it alternate. And then we have x to the 2n plus 1, that's going to give me all the odd powers, divided by the same thing factorial, right? So we have 3 over 3 factorial, 5 over 5 factorial, et cetera, et cetera. And what we're going to do is I'm going to start. So we'll see the first few that we actually just saw, right? So here are the first few we just saw. Now, how long do you think this is going to work? Do you think it's going to stop at like 2 pi? That'd be a good guess, because that's a period. No, they're still doing pretty well. Look at that. Look at how well this polynomial fits in. And I kind of like to do this. I like to turn off the sine wave. This is a polynomial, right? This is a polynomial that has this weird, like it's got a bunch of zeros. It starts up, it ends down. But what's happening is as I continue to let k get bigger and bigger, as I do more and more terms, look at, I mean, you couldn't tell the difference between this and the sine wave, right? This is at 30 terms, right? If you zoom out a little bit, eventually Desmos gets frustrated. Desmos will stop. I think it's around 50 terms. It starts to freak out a little bit. It just can't do the computations anymore. But this is one of those power series that actually converges for every single value of x. If you let this go off to infinity, I think at some point it's going to stop liking me. I don't remember when it happens, but it kind of starts to do weird things on the fringe. There it is. But if you let this go off to infinity, this is actually an exact equality for all real numbers, which just blows my mind. So the sine wave is one of the examples where it will actually work for every value of x. So you could use this series, as long as it was infinite, to approximate like sine of 20 pi. It would actually work perfectly if you had an infinite number of terms, which kind of is crazy to me. I think that's incredible. So let's take a look at cosine. Cosine is going to be very similar. So I graph the cosine function. And here we have all the even terms, right? X to the 2n divided by 2n factorial. That's going to give me all the even powers, and it's still alternating, right? Positive first term, and then we go negative, positive, negative, positive. So we're only perfect right at 0. And if we start to increase here, there we go. So cosine is all even powers. That's why we always have the same end behavior on both ends, either both going up or both going down. But as we see, just like sine, if I increase the number of terms, it is exactly perfect, right? It is exactly perfect. This is right where it starts to freak out. You can see it's starting to break up a little bit. But I always thought that this is just absolutely beautiful, that you can create a polynomial that perfectly mimics the entire cosine wave from negative infinity to positive infinity, or a sine wave that does this really well, which is kind of cool. All right, I got one more thing for you. So we talked about how this is the Maclaurin series, right? The Maclaurin series is centered at 0. What if we didn't want it centered at 0? So first question is, well, why wouldn't we want it centered at 0? It seems like everything's worked out just fine. And with sine and cosine, it works everywhere, so who cares, right? Well, what if we wanted to approximate like sine of 22? 22 is pretty far away from 0, right? 22 is not very close to 0 at all. So we might want to like center it at, I don't know, what would that be, like 7 pi? 7 pi would be kind of close to 22, right? Excuse me. So we have this formula that basically does it at any other value. And this actually works for 0 as well. So this is the formula for the Taylor series centered at x equals a. We have f of a, f prime of a times x minus a, f double prime of a, x minus a squared. So the difference is, instead of f of 0 every time, we're doing f of a. And then instead of being centered at 0, remember this is like a shift, right? This is like a shift either to the right or to the left by a units, depending on if a is positive or negative. And what this does is it does a nice job of mimicking the function somewhere else. So things that people tend to forget. They tend to forget that you have to plug a into the function instead of 0, right? So if you want to center it somewhere else, it's got to be the a is being plugged into the function, whatever that center is. And then they always write x. They write x and x squared and x cubed. You've got to remember the x minus a. So in sigma notation, sum from 0 to infinity, the nth derivative of a times x minus a to the nth power divided by n factorial. So this is good at approximating a function near a instead of near 0. Now again, you could just plug 0 in for a here and you would have the Maclaurin series, right? You would have f of 0, f prime of 0, f double prime of 0. But this is just if you wanted to mimic it somewhere else. So I've got one example that's already written out for you, and you don't have to write this down if you don't want to. But I'm just showing you if you wanted to center a Taylor series for sine x at pi instead of at 0, you just plug pi into all the derivatives, right? So you have sine of pi, derivative of sine is cosine of pi. And you have negative sine of pi, negative cosine of pi. And what happens here is, so all the sines are going to be 0 again. the cosines will all be 1 or negative 1, right? So cosine of pi is negative 1, so we start with a negative x minus pi here. The sign disappears. And then the next term that we're going to have is one that's in the negative cosine of pi here. That's going to be a positive 1 times x minus pi cubed over 3 factorial, and then minus x minus pi to the 5th over 5 factorial. So it looks like we are alternating. So we got negative 1 to the n plus 1 because the first term is negative. That's why it's not just to the n power. I need the first one to be odd. And then we have x minus pi to the 2n plus 1. That gives me all the odd powers divided by 2n plus 1 factorial. And if we look at the graph of that, I promise this is the last thing. Here's our sine wave. And here is the setup I have for it, right? This is the exact sigma notation that I had in the PowerPoint. So we notice that right away it's perfect at pi. It's not perfect at 0. And as I start to increase this, it's going to make nice polynomials that are centered at pi, right? And once again, if you went off to infinity, it would perfectly do it. So maybe sine isn't the best example to use because it's going to be great everywhere if you go off to enough terms. But if you had something that only was good between negative 1 and 1, and you wanted it to be good at 6, you would have to shift it. You would have to shift it over to 6 to be a good approximation around that number. So this one though, as you go, it's still gonna do a nice job approximating the entire sine wave. It's just gonna be centered at pi instead of centered at 0. All right, this has been a marathon. You guys have been great. I love you guys. That's why I'm here. Have a great day. Look forward to coming back and seeing you in the next video.